Hello everyone and welcome back. In this video, I'll be deriving an expression for the electric field at any arbitrary point inclined at an angle theta with respect to the center of a dipole, of a point dipole that is. And so, like the previous 2 or 3 videos, let's just begin with a small diagram of our dipole over here. So that's our dipole. So this is a minus q, plus q, and we've got an arbitrary point P over here that is inclined at an angle, say suppose this is O, which is the center of the dipole. We can say that this angle, this point P is inclined at an angle theta with respect to the center of the dipole. And this can be points A and B. But before we proceed any further, let's actually think about how we would go about finding the electric field at this point. Because remember, the electric field is actually a vector quantity, and as we keep changing this angle theta, the orientation of points, charges plus q and minus q with respect to this is will keep on changing. So we can't simply find a general expression by finding the vector substitute to plus q and minus q, because again, as angle theta changes, the orientation changes, and so that really won't be possible. Moreover, the electric field that we have over here, that is E is equal to minus dV by dr. The electric field is a vector quantity, but the potential that you have at a given point is actually a scalar quantity. So how exactly is it that you're differentiating a scalar quantity and then suddenly you have a vector? And again, like the direction that we're differentiating against is also not really very clear. And so the answer to all these questions that arise is basically working with vectors in single variable calculus simply does not work out. It's not legal. We need to define a separate field, that is multivariable calculus or vector calculus, to really work with them properly, because what we've been doing till now is whenever we needed to work with vectors, we would usually resolve them into one-dimensional components that we would give them either perpendicular, like we would resolve a two-dimensional vector into say a y component and an x component, and then differentiate it or then integrate it. So it's not really possible to do all of this in single variable calculus, and hence we need to work with multivariable calculus. But obviously, that is far beyond the scope of this video. So I'm going to do a sort of a workaround, I guess. It still does make use of partial derivatives, but as you will see, it's not very different from the idea that you have built in single variable calculus. And especially if you once you see what exactly constitutes, I think it becomes very clear why exactly we have chosen to do partial derivatives and why exactly we needed to use them. So without further ado, let's begin, I guess. So over here, what we intend to do is we intend to find the magnitude of any two perpendicular components, and then find the root of the sum of their squares, like we do with any other vector quantity. Suppose if we had a vector quantity over here, I'm going to say suppose we had a vector quantity over here, suppose say vector A. What we can normally do is that we can resolve it into say perpendicular components AY and AX, and then find the sum of the squares, and we'd find the magnitude of A. But over here, simply finding components along y and x directions are not very convenient, like I said, because we can't really define any useful relations, or we can't really differentiate or integrate properly along those lines. So what we instead do is we still do define perpendicular components, but they're not along the directions we think that they are going to be. That is, we define perpendicular components along the radial line of sight, like this, and a perpendicular component that is transverse to this line, or that is perpendicular to the line of sight. Right, so what this means is that we're going to find one component along the radial line of sight, so this is along R, you could say, and another component along this, and then you're going to find the square, that is the net vector basically. And so this somewhat, or like this, would be the magnitude of the electric field, like this. And so we can see that this electric field would be inclined at an angle alpha to the radial line of sight. So with this figure in place, we can finally begin to find the component along the radial line of sight and the component perpendicular to the radial line of sight, which we will call the transverse direction. So before I begin actually talking about a partial derivative, like I'll briefly state what these components actually will be. So I could say that ER, that is the component along the radial line of sight, is equal to minus del V by del R, where del V and del R are used to indicate the fact that we're taking the partial derivative instead of simply dV by dr, which would be for a regular derivative. And I will also add a small r over here to indicate the fact that the dr change in dr is along the radial line of sight. And I will denote the second component by et, which is along the transverse direction, and this will be equal to again minus del v by del r, because that is the definition of the electric field. But in this case, del r, or you can say dr, will be along the transverse direction. So the change in length that you see, the dr change in length, that will occur along this direction. And in the case of the radial line of sight, the dr change in length will occur along this direction. But before we go any further, let's talk about what a partial derivative actually is. And you might have already understood a bit of what it actually is with me talking about the differentiating only along either say the dr is along this part or dr is along say this part. So let's talk about a partial derivative, right? And now so far in calculus, you've usually encountered functions of the form say z is equal to f of x. That is, functions that are dependent only on one variable. And you can take the derivative of these pretty easily. That is, the derivative of z is simply dz by dx with respect to x, of course. But what if you have a function, suppose z, again, that is dependent now on two variables, say x and y. So in this case, you can't simply differentiate because with respect to one variable, because the function itself is dependent on both the variables, and you can't treat y as a constant while you're differentiating regularly, that is. So instead, what we do is we choose any one particular variable to differentiate with respect to, and we keep all the other quantities constant. And we denote this by calling it a partial derivative like this. It is del z by del x. That is, if you're differentiating with respect to x, while we keep all other variables that the function is dependent on constant. So in this case, we will be keeping y constant, and where we're differentiating with respect to y, that is, if I have to write del z by del y, in this case, x would be constant. And this might actually seem a bit, I guess, not very logical, but once you look at the physical scenario over here, it makes a lot more sense. Because in this case, we have V over here, that is, if I were to say the potential is a function of both r, that is the radius or that is the distance of the point from the center, and also of the angle theta at which this point is inclined with respect to the center. And as for y, it is a function of both r and theta. Well, that becomes clear from the formula for the potential due to an electric dipole. So that v is nothing but at any point at an angle theta to the center, nothing but 1 by 4 pi epsilon naught v cos theta by r square. And clearly it is dependent on both theta and r. So again, since it is dependent on two variables, we cannot simply take the regular derivative. We can't simply say E would be equal to minus dv by dr. We will have to take the partial derivative. But what is the physical meaning of the partial derivative in this case is, well, it becomes clear when you go back to the figure over here. Now in this figure, when I take the partial derivative along the radial direction, what I mean is I'm keeping the angle theta constant and only differentiating along the length of the radius. So if I were to consider, suppose, a point P dash over here, what I want is the difference in potential between this point P dash and this point P, and divide that by the difference of length of these points, and then you would get the magnitude of the electric field. And of course, that's just the definition of the derivative as you take the limit as the length delta r tends to 0. But essentially speaking, I'm going to keep this angle theta constant, and I'm only going to increase the length to suppose say r dash to a point P dash, and then I will find the derivative in the regular manner, you could say. And similarly, when I'm taking the partial derivative with respect to the transverse direction, what I'm going to do is I'm going to keep the length r constant. So I'm going to go to suppose a point over here that is p dash dash, where such that I'm going to go in a circle such that the length is again constant, and I could call this length r again because well, it's a radius. And so the radius is being kept constant over here, that is a distance from the center. However, the angle theta is becoming angle theta dash. And when that happens, we are essentially taking the partial derivative since the radius is being kept constant, but the angle theta is changing. And so the manner in which we do this is simply taking the mechanics of taking the derivative is the same, that is, derivative of cos theta would still be minus sine theta. But the idea behind it is really not the same, that is, the partial derivative in its working might be the same as the regular derivative, but in the theory behind it, the idea behind it is not the same at all. So with this sort of explanation out of the way, we can finally begin doing the maths. So ER, as we have over here, is nothing but minus del V by del R, where del R is along the radial direction. So if I were to write ER is equal to minus del V by del R, where V is equal to 1 by 4 by P, 1 by 4 by epsilon naught P cos theta by R square, as we have from the previous equation. So we could further this, when we take the derivative with respect to the radius, because we are increasing the length, when we do that, we have this being equal to 1 by 4 pi epsilon naught minus 2 P cos theta by R cube. And so we can cut the negative signs, and the electric field along the radial direction is exactly this. It is equal to 2p cos theta by 4 pi epsilon naught r cube. However, when we differentiate along the transverse direction to find the field along this direction, we run into a problem because we haven't actually defined some sort of we could say some formula or some idea or notion of what the length along the transverse direction actually is. So to understand that, let's go back to this figure and think about what this length delta r along the transverse direction could actually be. So if I were to say some del r transverse, I know that the radius r is constant in both these cases, and I know that the angle theta has changed from theta to theta dash. So I can say that since this is an arc, I could say L, we know that L is equal to r, where the r is the radius times the change in the angle, right? So I could say delta r transverse is equal to the radius r times the change in angle, which I will call d theta. So that would be equal to d theta. So I could change this equation down here to, just a moment, this could instead be equal to minus 1 by r del v by del theta. Where we are changing the angle theta, we're keeping r constant, and there's an extra 1 by r down here because of what we just saw. So again, this would now be equal to minus 1 by r, and since we are differentiating with respect to theta, we have cos theta in the equation. That will become minus p sine theta by epsilon naught into r square. And so this is the equation of the electric field along the transverse direction. And just cut that. And so what we have is, along the radial direction, the equation has 2p cos theta in the numerator, and on the other side we have p sine theta. So the net electric field, the magnitude of the net electric field, would then be simply the root of the sum of the squares, because these are perpendicular components. So that would be equal to ER square plus ET square, and then we can take the 1 by 4 pi epsilon naught and the r cube out of the equation because they are common to both the terms. And so that will be equal to, and we can take the p out as well. So the only things inside the root that are left is basically the trigonometric terms. That will be equal to 4 cos square theta plus sine square theta. And if we were to further simplify this, we know that sine square theta plus cos square theta is 1. So this just becomes 1 by 4 pi epsilon naught p by r cube. And what we have is then 1 plus 3 sine square theta. And this right here is the magnitude of the electric field at any point due to an electric dipole. So again, a number of observations. We see that the field trails away or reduces as r cube with respect to distance, which is similar to what we got in the previous videos while we were deriving the electric field at the equatorial and axial positions, and which it should make sense because this is basically the general case of those two case specific cases. And talking about those two cases, we will find that we'll get the result when we put the angle theta is equal to 0 and angle theta is equal to pi by 2. Okay, I just noticed something. This is actually cos square theta, so that's, yeah, so it's actually cos square theta, not sine square theta. Right, so when we put angle theta is equal to 0, that is, which corresponds to the axial position, we'll find that theta is equal to 0, so cos theta is equal to 1, which should be 1 plus theta is 4, and this should be equal to 2p by 1 by 4 pi epsilon naught r cube, which is the equation we got in the previous video. And also when we put theta is equal to pi by 2, this will become 0, which will then reduce to p by 4 pi epsilon naught r cube, which is the equation for the magnitude of electric field at the equatorial position. So we have now verified this equation by checking it with the extreme cases that we have derived in the previous video. But again, the electric field is a vector quantity, which I have stated numerous times throughout this video. And so what about the direction? This is only the magnitude, yeah? So to get the direction, what we need to do is we need to again go back to the figure. And what we have essentially done over here is we have found this component over here, you could say, that is the transverse component, and this component over here. So clearly, tan alpha over here would be equal to, you could say, E r by E t. So keeping this in mind, essentially the angle that the electric field vector makes with the radial direction is given by tan alpha is equal to Er by Et. And so if we find this ratio, we will find tan alpha, and then alpha, well, with alpha we'll basically get the direction of the electric field. So tan alpha is equal to, so I will not write the constants that are common to both the equations, that is p and 4 by epsilon naught r cube are common to both equations. What I'll write instead is simply sine theta by 2 cos theta. So this is nothing but tan theta by 2. But this doesn't mean that the angle alpha is half the angle theta, simply that the tangents are half. So instead, alpha is then equal to tan inverse of tan theta by 2. So with this, we finally know what the magnitude of alpha is, and remember, alpha is the angle at which the net electric field is inclined to the radial direction. And since we know that, we know what its direction is, and because of that, we have effectively found the net electric field created due to a point dipole at any point. So with that, we've finally come to the end of the video. I hope you learned something new, and thanks for watching.